In part 1 of lecture 4, we will discuss what is a process and switching processes. In the Stone Age of computing, computers ran one program at a time. This one program had all the resources of the computer at its disposal, and the computer's whole raison d'etre was to execute that one program. And if you were still running an older PC with DOS, your computer would not be any different. But computers don't work like that anymore, not even PCs. Computers multitask, performing more than one task at a time. They can print one document while you are editing another. You can download an MP3 while you're playing Minesweeper. Your computer can even interrupt you to let you know that you've gotten a new email. But this complicates the computer's ability to keep track of everything that it's doing. This is where the concept of a process comes in. A process is the act of executing a program. The very fact that we can keep track of the instances of different programs being run concurrently within the same time frame allows us to keep track of all the activities that a computer is juggling at once. Harvey Deitel, in his classic operating systems textbook, gives these various definitions of a process. But they all come down to the same thing. A process is the act of executing a program. If the same program is being executed separately by two users, with each instance being separately scheduled for the CPU, with different users owning each instance, that's two processes. If one user is running two separate instances of Notepad, that's two processes. And if 5 users are each compiling C++ programs simultaneously, that's 5 processes. On a single processor computer, only one process can actually be active at a time. The process that actually has control of the CPU is said to be running. Before it is actually in control of the CPU, it may have to wait its turn. These processes, the ones that are able to use the CPU, but have to wait to get back into it, are said to be ready. The ready and running processes are both in a position to make productive use of the CPU if they have control of it. But processes that are waiting for some event to happen, such as a print job to finish or a disk operation to be completed, are not in a position where they can make productive use of the CPU. We say that these processes are blocked. That is, that they are prevented from using the CPU until some event takes place which allows them to use the CPU. When these processes begin their lifetime, they are initially ready. They may get the use of the CPU immediately, or they may have to wait a while for it. We say that the process is admitted, that it joins the other processes that are ready for the CPU, but are waiting for it. When these processes get to use the CPU, we say that they are dispatched. Once a process is running, it will continue until it needs I/O of some sort, until it is finished running, or until the operating system decides that it has used enough time. If it is sent back to wait for another opportunity to use the CPU, we say that the process had a timeout. If the process is waiting for I/O, the operating system blocks it, and it is blocked from the CPU until the I/O operation is complete. Once the operation is completed, there is a wake-up for the process, and it is returned to a ready state, where it waits again for the CPU. A multitasking computer is able to look as if it is doing several tasks at once, because it can switch from one process to another and then back again faster than the human eye can notice. But in order to switch from one process to another, it needs to be able to keep track of the machine state of each process that is in the middle of execution. The information that defines a computer's state, register contents, memory contents, and the instruction that it is going to execute next, must all be stored so that we can continue the process exactly as we left it. It is a little like the use of still cameras in movie making, because scenes may be shot many times, and the actual movie may use portions of different takes of the same scene. Movie makers have still photographers take pictures before, after, and sometimes during scenes. This allows them to know exactly who and what was where at various times during a scene. This allows them to recreate a scene more accurately, and it looks as if the whole thing were filmed in one take. We need a similar means of recording the action. That's what we use the process control block for. It contains all the data relevant to the process: register contents, program counter, where in memory the data is stored, the files that were opened by or for the process, as well as miscellaneous accounting and status information that the operating system may need for its own purposes. When we switch from one process to another, the first step is saving all the information regarding a process in its process control block. After the operating system does whatever work it needs to do, it can load the new process's state. This means that register contents, program counter value, and so on now reflect exactly where process B left off before it timed out or was blocked. It is able to continue execution as if it never lost control of the CPU. Between the time that process A surrendered the CPU to the operating system and process B took over, the CPU belonged to the operating system. The operating system uses this time to do whatever chores are asked of it. This can include updating the clock, scheduling disk operations, and so on. But since the time is not being used by user processes, this can be viewed as purely overhead. For this reason, we try to get the operating system to do its work as quickly as possible, because we would rather have the CPU time used by user processes than by the operating system. As process B executes, one of several things may cause the operating system to take over. Process B may have used up the time that it is allowed. There may be an interrupt signaled by one of the computer's devices, such as the printer, or a disk drive, or the clock. Process B may have issued a system call. But in any case, the first thing that the operating system, when it takes over, will do is to save the process B's state in its process control block. We will assume that it is not the process that is restored when the operating system is finished. We will assume that the operating system will restore process A. As the operating system cedes control to process A, it reloads its state using the information saved in the process control block. As the operating system returns control to process A, it will resume operations. If it had timed out, it will continue as if there had been no interruption. If it was waiting for I/O, it will continue as if no other process had control of the CPU while I/O was being performed. A context switch is defined as the chore of saving a process's state so that another's state can be loaded. This is the exact activity that we have just described. How long this will take varies depending on the computer's hardware. Typical times for a context switch may vary from a microsecond to a millisecond. Given that nothing useful to users is happening during a context switch, we want these to be as fast as possible.